I want to do a couple of other things before we actually get into our full discussion today. And this is to help you better prepare for other coursework you might have. I didn't usually do this. I started doing this a couple years ago based on feedback from former students. I defined velocity as the rate of change of position. And in its differential form, we write it like this. dx dt is considered a differential. That's the fraction. It is the differential expression of velocity. I'm choosing my language well because in this case, I believe language does matter. Unlike jackets and hoodies, where I think that language is less consequential, saying that I need you to use the differential form of a variable means something very specific. Velocity is how fast you're traveling and in what direction. But it has a differential expression, dx dt. In the same way that acceleration is the rate of change of velocity, it too has a differential expression, dv dt. Now, the differential expression says something about what acceleration is. It's about how another variable changes. Now, that might not sound like much, but in the future, you might be greeted with an expression that looks like this. This doesn't look like much. On the left side is a constant times acceleration, and on the right side is velocity times time. What this expression says is that the faster you go, the more you accelerate. Right? This side, if this number gets bigger, then the acceleration must also get bigger if m is a constant. Do you guys see that? Okay. I'm bringing this up early. We will actually see this again in several months because acceleration is related to velocity. This is an expression that you will get if you consider the way air resistance works. The force from air resistance is proportional to how fast you're going. If you double your speed, you double how much air resistance you experience. One of the things you'll be required to do is come up with an expression for the velocity as a function of time. Well, that begins by creating a differential equation. So one of the first steps is to create a differential equation, which sounds way more complicated than it is. In this expression, you want to replace one of the variables, of which there are two, with a differential that could then be used to solve the function. Well, there's nothing I can replace for v that would introduce a, but there is something I can replace a with that would introduce v. I have replaced a with its differential function, which creates, at that moment, a differential equation. Now, a differential equation is nothing super fancy. It's an equation with a differential in it. In fact, this is what's known as a first-order differential equation, because it has a differential in it that is the first derivative of a function. Now, you've heard about first order or order in polynomials, like right? This is a second-order polynomial, or I think you learned second-degree polynomial, because I have a square in it. So it is the highest exponent. X must be the functional variable. So I would consider this a second-degree polynomial. We deal with differentials in the same way. Now, if you don't understand where I'm going with that portion, consider this. I have velocity in terms of the differential of position. It's quite plausible that I could rewrite this as d dt of dx dt. Now, symbology is important, but the symbology starts to get a little bit absurd. In calculus and even in physics, the way you express this, We're saying that this is a second order differential. Now, it's kind of stupid if you look at it closely, because why would the d's be squared? D doesn't represent a variable, it represents a change in a variable. The dt being squared may be if it's the whole thing, but I want you to understand that the moment I went from here to here, the symbology gets confused. So I want you to just note that this is symbology. That means to take the derivative of a position with respect to time and then take the derivative of that result with respect to time. It's the second derivative with respect to time. So if I write that here, that makes this a second order differential equation. In fact, I could go as far as to write it like this. A second order differential equation. It has a second derivative and a first derivative. Symbology. Now, you can probably see right away that this can become pretty cumbersome. So there are shorthand notations for these, and some schools expect that you know them. UCF, UF expects that you know these, but it's not really taught in our high schools. Putting a single dot over a variable is a way of representing the first derivative with respect to time. The dot is specific in that it's with respect to time. So if you see x dot or x double dot, we're talking about the first derivative and the second derivative. It's a shorthand notation, and that shorthand notation is used quite a bit in other schools. We don't teach it in ours, but I do believe it's appropriate that you have seen it, or at least have had it, kind of expressed to you. So when your professor starts writing x dots on the board, first day of physics or calculus when you go to college, don't be alarmed. And if you don't know what a symbol is, you should ask. Right? It's not your responsibility to remember all of it, especially if it wasn't something that was taught. Now, some of you have had calculus, and there's other expressions too for derivatives. Right? Function notation. Some of you know that you're going to be doing this in calculus, indicating that the prime means first derivative. Be careful. This and this aren't the same. The dot is more specific and means with respect to time. This prime right here means to take this function and find the derivative with respect to x. The x in there is telling you which variable you're taking the derivative of. So g of x is just a different function that still has a functional variable x in it. So g double prime of x would be the second derivative of that function. Again, more symbology, all representing the same thing. So when you leave this room and you start doing this in other classes, pay close attention. What you may think you know, make sure the symbology that they're using is reflective of what you think it is. I'm trying to be very careful, but ultimately, I'm only going to use that and that in here. I am going to stick with drawing it all out and making it all very explicit. I won't be using any shorthand in here, and they won't be using it on the AP exam either. This, however, all over the Calc A, B, and BC exam. You will have to understand that kind of functional derivative. All right. I want to move on, and I want to kind of pick up where we left off yesterday. Yesterday, we did the derivative of this function, right? And we found that it gave us, not surprisingly, this function. We may not have gone much further, but you should be able to take the derivative of this function. You should be able to find dv dt. What it should yield for you is a function that describes the acceleration. And it shouldn't be a surprise. Since we did something like this yesterday, let's take the derivative of both sides of that velocity function. I'm going to work in a t to the 0, because we're going to need that. We will distribute the derivative And when we do so, I hate writing all this out because it feels monotonous, especially when I've done it for a couple of hours. But I know that you guys probably still need to write it all out right in the beginning. By the end, we won't be today. Taking the derivative of a polynomial. Just a brief reminder, I put it up on the board, the polynomial method. When dealing with different functions, each different type of function will have a different method to take its derivative. Polynomials, pretty easy. I put it on the board. You'll need to know 4 different methods. This is just one of them. You'll need to know the trig functions, the exponentials, the logarithms. But the polynomials are pretty easy. So if I have a polynomial, and this is one, I just follow this procedure. What's inside the black box, don't worry about it. We're just going to skip over that. I'm just going to tell you it works. I'll let calculus show you why it works. But that means that here, I take the implicit 1, bring the 1 down, and I get a to the 1 times t to the 1 minus 1. Plus v naught times, I take the 0, bring it down, times t to the 0 minus 1. And this gives me what we knew would be the answer. 1 times t to the 0, which is just 1, so all that's a. And the other one, the 0 obliterates everything there, so that's it. Now, this shouldn't be a surprise. We started out with an equation we knew was generated from a constant acceleration. It makes sense that at the end, the acceleration is a constant. But it's appropriate for you guys to know that this could be generated from calculus and not from algebra, which is why I started with this function, because we have confidence in this structure. We've done some stuff with a constant acceleration and shown that these things are representative of the motion of an object. We've plotted it and everything to kind of verify that it represents reality. So today we're going to go on to more complicated forms of motion. What needs to be done? I want to show you what my expectations are. This is an expression for position. I imagine a problem where I say to you, find the velocity of this object when its acceleration is 0. I'll say that all over again because this is what the problems will be like. If this is my expression for position, then in this expression, I am likely to ask something like, find the velocity of the object when its acceleration is 0. All right? Everybody understand what the question, or at least know what the question is? Your first job will be to find an expression for the velocity and an expression for the acceleration. And you should be able to do this because we've practiced. So let's start. Let's find our expression for the velocity. We're going to do so by taking the derivative of both sides of the position function. Now, in the beginning, I'm going to be very verbose and write everything out, and I'm slowly going to pull back on that, all right? But right now, I'll be very verbose. I'm showing the symbology of taking the derivative of both sides of an equation. The left side we have an answer for. We know that the derivative with respect to time of position will be the velocity, so I can go ahead and sub in v for that. The right side, I have to use the distributive property. So I'll pull the constant out, but that'll be d dt of t cubed minus 6 d dt of t squared plus 9 d dt of t plus 4 d dt of, there's an implied 1 there. So I'll forego the implied 1 and replace it with t to the 0 power. t to the 0 power is the implied one. We need a polynomial, and if it starts with t cubed, any constants are t to the 0 as part of the polynomial. Now, your next step is to use the polynomial method to find each term's derivative. So, it says to take the exponent and bring it down front, and then subtract 1 from the exponent. So the differential symbol leaves, and I have the result using the polynomial function. Similarly, I'll bring the exponent down front, subtract 1 from the exponent. There's no exponent there, so that means that the exponent is 1. Bring the exponent down front, subtract 1 from the exponent, and I have a 0, so bring the 0 down front, but that's going to obliterate anything and zero out that function. And that should make sense. We're finding the rate at which each variable changes with respect to time. A constant doesn't change with respect to time. So the rate at which it changes is 0, which is why all the constants get zeroed out when you take their derivative. Now, the last step here is to do your algebra. And that part should be cake, right? 2 times 3 is 6t squared minus 12t plus 9. All right, we now have an expression for the velocity. We have created the expression that tells me the slopes of my position graph. And the slope of position is velocity. This is all of the velocities. Not done yet. You need to create all 3 functions. So the next function is going to be to take the derivative of the velocity with respect to time. That means taking the derivative of this whole function with respect to time. Again, I'm being very slow and deliberate. This is for your benefit, not mine. I know how to do this. So I'm going to continue to be nice and deliberate. Minus 12, thank you. So, slow and deliberate. Bordering on tedious. Just FYI, anybody who's had calculus would never write all of this out, okay? I'm writing it out now so you have very complete notes at home for when you have to do your homework. But I would never write any of this out. And I won't expect you to be doing it either. Okay, I'm just doing it now. I'm also not talking it out anymore. And do your algebra. Is everybody caught up? Everybody good? All right, so we've done all the work. Now you can do the problem. The problem was to find the velocity when the acceleration was 0. Now I assume, and I know that I'm saying a lot, I assume I don't have to do that, right? That you guys could do that. You could find what happens when the acceleration is 0. Right? Plug in 0 for acceleration and get 0 equals 12t minus 12. Do the math and find out that the acceleration is 0 when t equals 1. And now your next job is to find the velocity at 1 second. So v equals 6 times 1 squared minus 12 times 1 plus 9. Not asking too much here, right? So saying that I want you to find the acceleration, find the velocity when the acceleration is 0, is really just about making sure you can do the derivatives and that you understand how these things are related. There's any number of things that could be asked. Find the velocity when the object passes through the origin. Well, that would be setting the position equal to 0, finding t, and plugging it into velocity. Find the acceleration when the velocity is 0. All right, well, that would mean finding when the velocity is 0 and plugging it into the acceleration. The point is, you need to get an expression for the velocity, acceleration, and time. Velocity, acceleration, and position. And utilize what you know about acceleration, velocity, and position to find times when those things occur. I also want to emphasize, we're dealing with functions that aren't just ones that are easy, right? You know, I don't know what I just did there. The t cubed function, something like that, right? Could be, because it's a t cubed. I bring that up because it's got a local maximum and a local minimum. It wouldn't be out of the question to be asked, what is the maximum velocity on this interval? Right? Because these are things that we can do. And if you've never done these before, we'll practice a little bit. It's not a big deal. Mostly it's about generating these functions. A few other things I want to point out here too. If you look at the functions that we just did, get all this stuff out of my way, I don't need it. The 4, that's got to be the initial position, right? That will be the position when the time equals 0. The 9, what does that got to be? Initial velocity. What's the 12 got to be? The initial acceleration. Yeah. These represent the position, velocity, and acceleration at time 0. These are called boundary conditions. Also, initial conditions. Calculus tends to use this word. I tend to use this word. They both mean the same thing. They represent boundaries on your problem. And the boundary condition could be the position at time equals 4 seconds, and you'll have to figure out what the position is at time equals 0. Initial conditions, though, generally mean the conditions at time 0. But boundary conditions can be at any time. I bring it up because if you start with acceleration and attempt to work backwards, you realize you've lost something, right? When the derivative was taken to create the acceleration from velocity, we lost this number. So if you start with acceleration, you don't know what the initial velocity was. In the same way, if you start with velocity, you don't know what the initial position was. Remember in class, when we did the first velocity graphs, we couldn't say where the object began. You had to ask, where was the object at time 0, because it wasn't part of the velocity graph. That's because it is lost when you start taking the derivatives. Now, it shouldn't take you long to realize eventually we're going to start somewhere else, and you're going to have to both go this way and this way. That's got to be a clear part of where this course is going to go. So let's do one more practice, and then let's start kind of picking up the picture that I have everybody on board, but as to where I really would like to go. So we'll do one more straightforward practice. Find the velocity and the acceleration function, please. And I love your attention to detail, but let's face it, you're not going to write all that out. You don't have time. It's nice to write all the symbology out. We're going to take the derivative of this function. Let's just look at each term and apply the polynomial method. I need to bring the exponent down and subtract 1 from the exponent. Writing all the steps in between, yeah, that's the way, that's what's happening. But the result is this. All right, I've taken the derivative of the first term. I'm going to take the derivative of the second term. It's going to be 2 times 3, right? 3 is already out there. I'm going to bring the 2 down. So it's going to be minus 6 t to the 2 minus 1, just t. Next one, well, there's an implied 1 here. I'm going to bring the 1 down, multiply by 6. That's going to be minus 6. T to the 1 minus 1 is t to the 0. It's good, it's 1. Plus, well, that's it. We're done. Right? The 2 is t to the 0. I bring the 0 down and it annihilates the whole term. Writing all the steps is great. I do that. The truth is, I think this is just as good. Next level, 3 times 4 is 12 to the t squared. There's an implied 1 here. 1 times 6, negative 6. T to the 1 minus 1, t to the 0. And a derivative of 6, 0. It's gone. That's it. This is all I'm actually expecting to see. In fact, I'm not even sure I need to see this stuff. It is okay to show that amount of work. We've got 9 minutes left. I want to go one step further, but is there anybody who needs to see another practice? All right. Could you do this one? Could you go this way? I know you can go this way. Walked around the room and saw a lot of people having success. Can you go backwards? Can you do the antiderivative? Now, if you've never done this before, if taking the derivative of the polynomial means bringing the exponent down and subtracting 1 from the exponent, then taking the antiderivative has to be the opposite. So if my term is ax to the n, and I have to take the antiderivative, I'm going to add 1 to the exponent, and I'm going to divide by the new exponent. That's taking the antiderivative. Now, still polynomial, it's going to create what is there before you take the derivative, or try to. So for example, I have t squared. Well, I'm going to add 1, t to the 3rd. And now I divide by the new exponent, divide by 3. Now, what I'm left with, when I take 9 and divide by 3, and I get 3 here, is 3t cubed. Now, this should match up with what would happen if I took the derivative going back. Bring the 3 down, 3 times 3 is 9, subtract 1 from the exponent. T, add 1, I get t squared. Divide by the new exponent. There's no t next to the 3, so that's an implied t to the 0. Add 1 and divide by the new exponent. Now, you're not done. when you're taking the antiderivative, remember there could have been a constant here. There could have been one, and it would have disappeared when we took the derivative. So you have to remember to put the appropriate constant in place. Calculus will teach you to just put a C there, but we know what this represents. We put in the symbology that we're using. This is the initial position. And of course, 2 times 9 is 18, t, and 1 times 4 is 4. Now, I do need to tell you something. I'm cutting a corner. There's more symbology, and I'm cutting a corner. Saying to just take the antiderivative leaves out a whole bunch of calculus. What's really happening is not just taking the antiderivative. Just like there's symbology for taking derivatives, and we talked about what that symbology looks like, there's symbology associated with taking the antiderivative. There's symbols that tell you that you need to take the antiderivative. It looks like this. First, we are trying to go from the acceleration to the velocity. So I put in the differential. This is the step 1, and letting my person know I want to go backwards. Next, I told you this is just a fraction. So you can split the derivative by multiplying by the denominator of the fraction. All right, now's the big thing. There's a symbol that means to take the antiderivative. It means more than that. For the time being, the symbol is called the integration symbol. One step in the integration process is taking the antiderivative. By putting this integration symbol, by taking the integral of both sides, it's like the opposite of taking the derivative of both sides. And it tells the person, like me, that, all right, I'm going to be taking an antiderivative there and an antiderivative there. Since there's no term here, the v tells me to put a v to the 0 power there. For the same reason that I put a t to the 0 power there. And now we just do the antiderivative process for in this case, a polynomial. I'm going to add 1 to that exponent, v to the 1, and divide by the new exponent. I'm done on the left. Go to the right. I'm going to add 1 to my exponent and divide by my new exponent. I'm going to add 1 to my exponent and divide by my new exponent. But we're not done. We have to put in the constant that disappeared. And if we don't know what it is, we use a placeholder to represent that expression at time equals 0. Now, I'm skipping some stuff, but these integrals are called indefinite integrals. Now, in the future, we might have what are called definite integrals, and we will be doing integration in this class, which means to take the antiderivative. There's placeholders here and here to put values for doing definite integrals. We'll learn about that later, but for the time being, we're just going to be doing what's called indefinite integrals, which means they don't have any boundaries. We just add a boundary statement. In this case, that boundary statement was putting in the appropriate variable here. All right, I have homework that goes along with this that I'll be posting the moment I have better internet access. There's not many, it's like 5 or 6. Please practice.